Okay, welcome to the lecture series number 6 on our video lecture series on Physics 2. So for today's discussion, we have a discussion on capacitors. So for this topic, we will be dealing with the following coverage. We have capacitors, capacitance, calculating capacitance, capacitors in vacuum, capacitors in series, capacitors in parallel, and capacitors in combination. Okay, so to start off, we define first what is a capacitor. A capacitor is any two conductors separated by a vacuum or an insulator or any insulator. We call this insulator that is being sandwiched by these two um, metal plates or metal conductors. We call this the dielectric. A capacitor is simply an electronic device that stores electric potential energy and electric charge. In circuit diagrams, a capacitor is represented by either of these symbols. Okay, so what is capacitance? Capacitance is the ability of a capacitor to store charge or energy. It is denoted by capital letter C for capacitance, and take note, you should not be able to confuse capacitance with coulombs. The international system of units for the capacitance is the farad in honor of the English physicist Michael Faraday. Now, the capacitance is defined as the ratio of charge over potential difference. In mathematical symbols, we have this relationship as C is equal to Q over V sub AB, where C here is the capacitance, Q is the charge that is stored in the capacitor, over the potential difference formed in the between the two metal conductors. Okay, so let's take a few examples. A metal sphere mounted on an insulating rod carries a charge of 6 nanocoulombs. When its potential is 200 volts, higher than its surroundings. So what is the capacitance of the capacitor formed by the sphere? Okay, so in this sample problem, 6 nanocoulombs is actually represented by 6 to the negative 9 coulombs. So divide this by 200 volts. You should be able to verify this in your own using your own calculators. So in the scientific calculator, this is supposed to be 6 exp negative 9 divided by 200 volts. That is 200 volts. This is equal to 3 times 10 to the negative 11 farads. Okay, so calculating capacitors in vacuum. What you see here in this illustration is the basic arrangement for a capacitor. We call this capacitor as the parallel plate capacitor. Now the arrangement goes like this. You have two metal plates, the upper plate and the lower plate. These two are made up of metals. Now what happens in this, the two metals is actually separated by a separation distance, small letter d, and the space in between the two metal plates is actually vacuum. Thus the name capacitors in vacuum. So the idea here is that when the two metal plates connected in a wire is subjected to a potential difference V sub AB or a voltage V sub AB, the forming potential difference causes a transmission of the charges from one plate to the other. So what happens is a charge is transferred from one plate to the other, thus making one of the plates positively charged and the other one negatively charged. Now Q here, as represented in the formula of C is equal to Q over V, represents the amount of charge that is stored in each of the in each of the plate. So Q there represent in the formula C is equal to Q over V. Q there represents either the amount of charge that is present in the positively charged plate, or it could also be the reference to the amount of charge that is stored in the lower negative plate. Okay, so this is the side view of the parallel plate capacitor. Now, since you have a positively charged plate on the upper plate and a negatively charged plate on the lower plate, now of course, since this would be charged, therefore it would be forming an electric field in between. So from the positive coming from the positive plate, ending up ending up at the lower plate. Now, the capacitance of a given capacitor, if you're going to look at the root word of the word capacitance, the root word of the word capacitance is capacity. So, indicating that a capacitor functions by filling up the capacity of the setup of the capacitor to a maximum amount for as long as the capacitor is subjected to potential difference or voltage V sub AB. So for as long as it is subjected to the potential difference, there would be a continuous transfer of charge from one plate to the other, forming the amount of charge that will be stored on each parallel plate. Now, how much charge will be transferred from one plate to the other? That depends on how much potential difference was subjected in between the plates and how much time it takes for the capacitor to transmit the charges from one plate to the other. Of course, this means that the longer you subject the two plates in the potential difference, the more charge will be transferred from one plate to the other. Also, if the amount of charge that would be transferred from one parallel plate to the other not only depends on the amount of the potential difference subjected to the two plates, not only on the time of the time it takes for the two parallel plates have been subjected to the potential difference, but also it also depends on how many electrons that are present in each of the plate that will be transferred, which basically depends on the physical features of the capacitor, particularly the separation distance and the area of the parallel plate capacitor. Of course, that this means that if you have a smaller area, meaning you have a smaller size of a capacitor, you will have lesser amount of charge that will be transferred from one plate to the other. Of course, in opposite, the greater the area of the capacitor, meaning the greater the size of the capacitor, the more charge that can be transferred from one plate to the other for as long as it is subjected to a given potential difference. Now, what happens now if the capacitor is fully charged or is charged? This means that there will be an established electric field in between, and therefore, just like what we have presented from the previous video lecture, two plates with charged parallel plates where there is a presence of an electric field in between, and whenever charge passes through the area of the electric field in between the two parallel plates, there is a tendency that the capacitor could store electric potential energy in between these plates whenever a charge transfers from one plate to the other. So therefore, this refers to the overall function of a capacitor. The function of a capacitor is to serve as a storage of electric potential energy. Much like gravity can be storage for gravitational potential energy. Now, for a capacitor in vacuum, we can have two forms of the equation for the capacitance. Instead of having C is equal to Q over V, V sub AB, we could also have the second form of the equation for the capacitance as epsilon sub O sub 0 times A over D, specifying that the relationship between the amount of capacitance of a given capacitor is dependent on the area of the parallel plate capacitor and the distance separation between the two parallel plates. Of course, C here, or the capacitance, is directly proportional to the area, so the greater the area of your capacitor, the greater the capacitance. Also, the capacitance is inversely proportional to the separation distance between the two plates. So that means the smaller the separation distance between the two plates, the larger the capacitance of the capacitor. Now, epsilon sub zero here is a constant, which appears also in our derivation of the our representation of the constant in Coulomb's law. Remember that K in Coulomb's law has the form 1 over 4 pi epsilon sub 0. So epsilon sub 0 there refers to the constant of permeability of free space that has the value 8.85 to the negative 12 farad per meter. Okay, so in the formula we have the following symbols. So A is the area of the plate in square meters, D is the distance separation between the two plates, Q is the amount of charge that will be stored in our capacitor, V sub AB is the potential difference in volts. Okay, so let's take a sample problem. The plates of a parallel plate capacitor in vacuum are separated by 5 millimeters and the area is 2 square meters. The potential difference of 10,000 volts is applied across the capacitor. So letter A, compute for the capacitance. So in the given capacitance is equal to epsilon sub 0 A over D. So this is the value for the epsilon sub 0. We have 2 meters square over 0.005 meters for 5 millimeters, and that gives us 3.54 to the negative 9 farads. Okay, so letter B, what is the charge on each of the plate? So for this, we compute for, we make use of the second form of the equation, solving for Q. So we have Q as equal to C times V. Okay, so this is equal to, we are given the value of the capacitance, that is 3.54 to the negative 9 farads, and we multiply this with 10,000 volts. This is 10,000 volts. Okay, so you should be able to verify this using your own calculators. So in the calculators, this should be 3.54 exp negative 9 times 10,000. So this should be equal to 3.54 but this is 3.54 to the negative this is negative 5, and the units should be coulombs. Okay, so next, find the magnitude of the electric field in the space between them. Okay, so try to recall in your in our previous discussion on electric potential and electric potential energy, the relationship between the potential and the um, okay, so I'll be finishing this first, and I will just be continuing the solution to the problem for the next video.